Hey, welcome back. If you found your way here at this hour, whether it's 10 past midnight, somewhere deep in the foggy territory of 3 a.m., or that strange no man's land between late night and early morning where time stops, I want you to know you've landed somewhere good. Pull the blanket up, get comfortable. Maybe close your eyes for a moment first, just to let the day settle. Because tonight, we're going to do something a little unusual. We're going to think about absolutely nothing, and I mean that literally. Before we dive in, if this kind of slow, thoughtful content is something you enjoy, the kind that takes enormous ideas and holds them up gently to the light, please tap the like button. It genuinely helps more people find this channel and videos like this one. And if you're new here, consider subscribing. These journeys happen regularly, and I'd love to have you along for future ones. Drop a comment and tell me where in the world you're watching from and what time it is for you right now. Midnight, 4 a.m., that drowsy golden window just before sleep. I always read those, and there's something quietly remarkable about knowing someone in Tokyo or Sao Paulo or a small town in Norway is sitting with the same questions on the same night. All right, let's begin. Tonight's question sounds simple. Deceptively, almost insultingly simple. Did nothing ever exist? Say it out loud. It almost sounds like a joke, like asking whether silence has a flavor, or whether darkness weighs anything. But I want to make you a promise right now. The more carefully you sit with this question, the stranger it becomes. The more you poke at it, the more it pokes back. Because when physicists, philosophers, and cosmologists actually attempt to answer it, seriously, rigorously, with the best tools available, they run into something they didn't expect. Nothing, as a concept, refuses to cooperate. It squirms, it shapeshifts. It turns out to wear several disguises, and each time you remove one mask, there's another underneath. And what's most unsettling of all is the growing suspicion, shared by scientists and thinkers across centuries, that true nothingness might not just be rare or hard to find, or hidden somewhere out beyond the edge of the observable universe. It might be impossible. So let's take that idea apart, slowly, carefully, and with as much wonder as we can carry. Let's start with the most ordinary version of nothing you know. Picture the inside of a kitchen drawer. Maybe it's that one drawer everyone has. The junk drawer, the place where dead batteries and mystery keys and takeout menus from restaurants that closed 3 years ago go to live out their days. Now imagine you've cleaned it out completely. Everything gone. You open the drawer and look inside. Empty. You'd call that nothing, right? But of course, the drawer isn't empty. It's full of air, oxygen, nitrogen, a small percentage of carbon dioxide, traces of argon, maybe the faint molecular memory of whatever was stored there before. If you could shrink yourself down to the scale of molecules and stand at the lip of that drawer, you'd be overwhelmed. You'd be in a crowd so dense it would make a rush hour subway feel spacious. So that's not nothing. That's just nothing we care about. Let's go further. Imagine a sealed metal chamber in a physics laboratory. Scientists have spent considerable effort and money pumping every last molecule of air out of it. Not a single atom remains. We call this a vacuum. And for a long time across most of human history, this is what people meant when they said empty space, an absence of matter, a clean, quiet void in which nothing exists and nothing happens. Even fairly recently, in the classical physics of Newton and his era, a vacuum was considered the closest thing to nothing that physically existed. Space was just the container, the neutral stage on which things happened. And empty space was the absence of things happening. But the 20th century had other ideas. Because when quantum physicists peered into that perfectly emptied chamber, they found it wasn't empty at all. Not even close. To understand why, we need a brief tour of one of the most powerful ideas in all of modern science, quantum field theory. In the classical picture, the one most of us carry around in our heads from school, the universe is made of particles, tiny, discrete objects with mass and charge that move around and interact. Billiard balls at the atomic scale. Light was a wave, matter was particles, and somewhere in between they sometimes confused each other. Quantum field theory throws all of that out and replaces it with something richer and stranger. According to QFT, the universe isn't made of particles at all. Not fundamentally. The universe is made of fields, invisible, continuous structures that stretch across all of space, everywhere, all the time, without exception. There's a field for electrons, a field for quarks, a field for photons, a field associated with every fundamental particle we've ever detected. And these fields are not confined to where the particles are. They exist everywhere in the universe simultaneously, like an infinite invisible ocean with many overlapping layers. When one of these fields vibrates in just the right way, when a ripple of sufficient energy passes through it, what we observe is a particle. An electron is not a tiny ball orbiting a nucleus. It's a ripple in the electron field, momentarily concentrated into something that behaves like a particle. A photon isn't a small package of light flying through space. It's a disturbance in the electromagnetic field, propagating outward from its source. Now here's where the vacuum becomes interesting. These fields can never, ever be fully switched off. Even at their absolute lowest energy state, what physicists call the vacuum state, they still fluctuate, they still ripple. They can't be perfectly still, because perfect stillness at the quantum level would require us to know both the exact energy and the exact timing of a state simultaneously. And the Heisenberg's uncertainty principle says that's impossible. The more precisely you pin down one quantity, the more uncertain the other becomes. It's not a limitation of our instruments. It's a fundamental feature of reality. The result, even in the emptiest space imaginable, the quantum fields that fill it are always whispering, always trembling faintly. Energy spontaneously rises and falls within the vacuum. And when a local fluctuation is large enough, it temporarily produces a pair of particles, one matter particle and one antimatter particle, flickering into existence together, existing for an almost incomprehensibly short time, and then annihilating each other back into the vacuum. They're called virtual particles, and while they can't be directly observed, their effects absolutely can. One of the most elegant demonstrations is the Casimir effect. Take two uncharged flat metal plates, place them in a vacuum, separated by an extremely small gap, a few nanometers. According to classical physics, with nothing between them and no charge on either plate, there should be no force. Nothing should happen. But in reality, the plates are pushed together, gently but measurably. Why? Because the virtual particles that fill the vacuum have wavelengths. In the narrow gap between the plates, only particles with wavelengths short enough to fit can appear. Outside the gap, the full spectrum of virtual particles exists. The pressure from outside is slightly higher than the pressure between the plates, and the plates are pushed together by the vacuum itself, by what we thought was nothing. The Casimir effect has been measured in laboratories to extraordinary precision. It is not theoretical. It happens, which means the vacuum is not nothing. It is a sea, a restless, fizzing, probabilistic sea of fluctuating fields and ephemeral particle pairs. It has energy, it has structure, it has behavior, and that's just empty space. All right, so the physical vacuum isn't nothing. Let's try to go further. What if we removed space itself? Not the stuff in space, not even the fields threading through space, but the geometry, the dimensions, the very framework in which distance and direction exist. No up or down, no here or there, no metric, no coordinates. Not darkness, because darkness is a visual experience and vision requires space, but the literal absence of spatial structure. Can we even think about that? This is where language begins to fail us in very revealing ways. Without space, there is nowhere for nothing to be located. Without time, there is no when for nothingness to occur. If you try to imagine absolute nothingness, no space, no time, no fields, no laws, no mathematical structure, no possibility, you find that your imagination keeps sneaking something back in. A dark background, a sense of waiting, an absence that is still, somehow experienced. Even the concept of emptiness requires a container to be empty. True absolute nothingness can't be pictured. Not because our imaginations are limited, though they are, but because the act of imagining presupposes a mind, which presupposes a brain, which presupposes matter, which presupposes a universe. Every attempt to visualize nothing ends up sneaking something through the back door. Gottfried Wilhelm Leibniz, the 17th century mathematician and philosopher who co-invented calculus alongside Newton, put this beautifully in a question that has echoed across 3 centuries. Why is there something rather than nothing? He meant it as the foundational question of all metaphysics. And despite everything science has learned since, it remains stubbornly, magnificently unanswered. Because there's a hidden assumption buried in Leibniz's question. It assumes that nothingness is a coherent alternative, that it was possible for there to be nothing, and therefore the existence of something requires explanation. But what if that assumption is wrong? What if nothing is not a road not taken, but a road that doesn't exist? What if existence is not the surprising outcome, but the only coherent option? We'll return to this. But first, let's follow the scientific story of where everything came from. Let me ask you something. When you hear the words Big Bang, what do you picture? If you're like most people, you picture something like a massive explosion, a giant fireball erupting in darkness, an enormous detonation blasting matter outward in all directions from a single central point. The universe born like a bomb going off in an empty room. That image is understandable. It's also almost completely wrong. And understanding why it's wrong gets us much closer to the truth about origins, beginnings, and the nature of nothing. Let's start with a historical quirk. The term Big Bang was never meant to be taken seriously. It was coined in the 1940s by a brilliant British astronomer named Fred Hoyle, who used it sarcastically during a BBC radio broadcast. Hoyle was a champion of a rival theory, the steady-state model, which held that the universe had always existed, was eternal and unchanging in its overall structure, and constantly generated new matter to fill the gaps left by expansion. He didn't believe in a universe with a beginning, so when he described the competing idea on the radio, he called it, dismissively, the Big Bang, a throwaway jab. The name stuck. The theory proved correct. Hoyle spent the rest of his career linked to a term he invented to mock an idea he opposed. Science is occasionally unkind, but the name has done real damage to public understanding ever since, because a bang implies an explosion, and an explosion implies a location, and a location implies pre-existing space for the explosion to happen in. None of those implications are accurate. Here's what actually happened, as best we understand it. In the 1920s, Georges Lemaitre, a Belgian priest who was also a serious mathematician, looked at Einstein's field equations of general relativity and noticed something no one had fully absorbed. The equations didn't describe a static universe. They described a universe that should be either expanding or contracting. Einstein himself had been so uncomfortable with this implication that he'd inserted a fudge factor, a cosmological constant, specifically to cancel out the expansion and produce a static universe. He later called this the biggest mistake of his life. Lemaitre didn't fudge it. He followed the math, and the math told him that if the universe is expanding now, then it was smaller in the past. Rewind the clock far enough, and everything we see was compressed into an unimaginably small, dense, hot state. He called it the primeval atom, a cosmic egg. Then, in 1929, Edwin Hubble gave him the observational evidence. Hubble was analyzing light from distant galaxies and noticed a systematic pattern. The light was redshifted, stretched toward longer, redder wavelengths, and the further away the galaxy, the more the light was shifted. This is redshift, and it means the source is moving away. Like the falling pitch of a receding train whistle, light from a source moving away from you gets stretched into longer wavelengths. Hubble saw this in every direction. Every galaxy was receding. The universe was expanding. Run that film backward, galaxies rushing together, matter compressing, temperatures rising. Until roughly 13.8 billion years ago, we reach a state of extraordinary density and heat. Not a thing inside space, but the origin point of space itself. And this is the crucial thing. The Big Bang was not an explosion in space. It was an expansion of space. Space itself was born at that moment. Time itself was born at that moment. There was no pre-existing void for the universe to explode into. There was no dark, empty room waiting to be filled. Space, time, matter, energy, and the laws governing all of them emerged together as a package. The balloon analogy helps here. Draw dots on the surface of an uninflated balloon with a marker. Those dots are galaxies. Now inflate the balloon. Watch what happens. Every dot moves away from every other dot. Not because the dots are crawling across the rubber, but because the rubber itself is expanding. Every dot is carried along by the medium it sits in. Now here's the critical implication. There is no center of expansion. Pick any dot on the balloon, and from its perspective, everything else is moving away, because space itself is growing uniformly. In our universe, wherever you stand, you'll see the same thing. Galaxies receding in every direction. It looks like you're at the center, but so does every other point. There is no center. There is no edge. There is no location where it happened. It happened everywhere simultaneously, because everywhere is the place where the fabric of space began to stretch. What actually happened in the first moments of this expansion? In the first fractions of a second, and we're talking time scales so small that calling them tiny feels like an insult to the word, the universe was a plasma of inconceivable density and heat. Temperatures in the trillions of degrees and climbing. Energies so high that matter as we know it couldn't exist. No atoms, no molecules, not even protons or neutrons. Just a seething, undifferentiated broth of quarks, leptons, gauge bosons, and forces that hadn't yet crystallized into their familiar modern forms. As the universe expanded, it cooled. Cooling allowed structure. Quarks slowed down enough to be captured by the strong nuclear force and assembled into protons and neutrons. About 3 minutes in, nuclear fusion ignited, and those protons and neutrons began combining into the first atomic nuclei. Mostly hydrogen, roughly a quarter helium by mass, and trace amounts of lithium. The universe was now a gas of nuclei swimming in a sea of free electrons, too hot for the electrons to settle into stable orbits. This phase lasted about 380,000 years. Then something beautiful happened. The universe cooled past a threshold. Electrons could finally slow down enough to be captured by nuclei. Neutral atoms formed for the first time. And with that transition, the universe became transparent. Light, which had been scattering off free electrons like sunlight bouncing through fog, could finally travel unimpeded. It streamed out in every direction. That light is still traveling today. We call it the cosmic microwave background, the CMB. It fills the entire sky with a faint, nearly uniform glow of microwave radiation, invisible to the naked eye, but detectable by sensitive instruments. Every direction you point a microwave telescope, it's there. incredibly uniform, but not perfectly so. There are tiny temperature fluctuations, ripples of 1 part in 100,000. And those ripples are the imprints of the earliest structures in the universe. The seeds of future galaxies, clusters, and cosmic filaments preserved in that ancient light like a fingerprint pressed into clay. The CMB was discovered in 1965 almost by accident by two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson. They had a highly sensitive antenna and kept picking up an unexplained background noise coming uniformly from every direction. They rechecked their equipment, they checked their calculations, they even cleaned pigeon droppings off the dish, thinking, perhaps hopefully, that biological interference was the culprit. The signal remained. It was the echo of creation, arriving from 13.8 billion years in the past, and it's considered one of the strongest pieces of evidence for the Big Bang model ever gathered. If the Big Bang was the beginning of space, does that mean it was also the beginning of time? Yes. And sitting with that answer is one of the most genuinely disorienting experiences available to a human mind. In Einstein's general theory of relativity, our best description of gravity and the large-scale structure of the universe, space and time are not separate things. They're woven together into a single four-dimensional fabric called spacetime. Mass and energy warp this fabric, and that warping is what we experience as gravity. Earth curves space-time around it, and the moon follows that curve, orbiting rather than flying away. If space-time began at the Big Bang, then time began at the Big Bang. Not just our clocks, not just our ability to measure time, but time itself. The dimension, the fabric, the medium through which change occurs. Which means asking what came before the Big Bang may be like asking what is north of the North Pole. Stand at the North Pole, try to walk north. You can't. Not because there's a wall, not because it's forbidden, but because north as a direction becomes meaningless at that point. Every direction from the North Pole is south. The concept runs out. Stephen Hawking loved this analogy. He used it in lectures and interviews for decades. Time near the Big Bang becomes like a spatial direction. It rounds off. There's no sharp edge, no moment you could point to and say, here is where time began, and before this, there was something else. The before dissolves, the way north of the North Pole dissolves. But here's where the honest physicist has to acknowledge a problem. General relativity gives us this picture of a smooth beginning, but it also breaks down at that beginning. At the singularity, the equations produce infinities. Infinite temperature, infinite density, infinite space-time curvature, and infinities in physics are not answers. They're mathematical SOS signals. They mean the theory has been pushed beyond the domain it was designed to describe. So we don't actually know what happened at the very beginning. Not because data is missing, though it is, but because our best theory runs out of descriptive power precisely when we need it most. The question of what came before or at the Big Bang is therefore not settled. It sits at the cutting edge of theoretical physics. And it's where general relativity and quantum mechanics are forced, reluctantly, into a confrontation that neither of them was built to handle. So, could the universe have come from something approaching nothing? Some physicists think the answer might be yes, and the mechanism might be quantum tunneling. In classical physics, barriers are absolute. If you roll a ball toward a hill, and it doesn't have enough energy to reach the top, it rolls back, full stop. But in quantum physics, particles aren't like balls. They're described by wave functions, probability distributions spread across space. And these wave functions can bleed through barriers that classical mechanics would declare impassable. A particle can appear on the other side of an energy barrier without ever having enough energy to go over the top. This isn't a metaphor. It's one of the most experimentally verified phenomena in all of physics. Quantum tunneling is how nuclear fusion happens inside stars. Protons tunnel through the electrostatic repulsion that would classically prevent them from getting close enough to fuse. It's also how radioactive decay works. It's the operating principle behind the tunnel diodes in your electronics. It is not exotic. It is ordinary at the quantum scale. Now, in the early 1980s, physicist Alexander Vilenkin proposed something extraordinary. He asked whether quantum tunneling could apply not just to particles, but to the universe itself. Could a universe tunnel into existence from a state of zero? No space, no time, no matter, no energy, through the quantum probabilistic loophole that allows small probability events to occur without classical permission. His mathematics suggested yes. In Vilenkin's model, the universe didn't require a cause in the traditional sense. No prior universe, no divine spark, no pre-existing conditions. Just the application of quantum probability to the question of existence itself. The universe arose because, in quantum mechanics, anything with a non-zero probability of existing will eventually exist. And the probability of a small, simple universe spontaneously tunneling into being, while vanishingly small, is not zero. This model raises a sharp question that Vilenkin addresses directly. If quantum laws governed the tunneling, where did the quantum laws come from? His answer is that mathematical and logical laws are not physical objects. They don't require space or time to be real. They're not things that exist inside the universe. They're the abstract structure within which any universe is possible. The laws of logic, the principles of mathematics, the framework of quantum probability, these may be prior to any physical reality. Not in a temporal sense, but in a foundational sense. The way the rules of chess are not inside any particular game, but are the condition for any game being possible. It's a view that blurs the boundary between physics and philosophy. Some scientists find it unsatisfying, others find it the most honest answer available. Either way, Vilenkin's proposal represents one of the most serious attempts anyone has made to trace existence back to its root, and to find, at that root, not an external cause, but a self-contained quantum possibility. Here's something that often surprises people. The Big Bang, as we usually describe it, the hot, dense plasma expanding outward, may not actually be the very beginning. There may have been something before it, something even faster, something so brief and so extreme that it shaped everything we observe today without leaving an obvious fingerprint. This is cosmic inflation, and it's one of the most important ideas in modern cosmology. By the late 1970s, cosmologists were wrestling with several puzzles that the standard Big Bang model couldn't cleanly resolve. The first was the horizon problem. The cosmic microwave background is almost perfectly uniform. Temperature variations of less than 1 part in 100,000 across the entire sky, which sounds like a small variation, but consider what it implies. Regions of the universe that are currently so far apart, they could never have exchanged so much as a single photon in 13.8 billion years. Not even communicating at the speed of light, somehow have nearly identical temperatures. How? How did they coordinate? How did they know to be the same? The second was the flatness problem. The universe appears geometrically flat. Parallel lines stay parallel. The curvature of space on large scales is essentially zero. For this to be the case, the density of the early universe had to be balanced against its expansion rate with extraordinary, almost unnatural, precision. An imbalance of even 1 part in 10 to the 60th power in the first second would have produced a universe that either recollapsed almost immediately or expanded so fast that gravity could never have assembled matter into galaxies. In 1980, physicist Alan Guth proposed a solution so elegant it changed the field almost immediately. What if, in a vanishingly brief instant after the beginning, trillionths of a trillionth of a second, space underwent a period of exponential expansion? Not the modest expansion we see today, something incomparably more dramatic. In less time than it takes light to cross an atomic nucleus, the universe would have doubled in size again and again and again, expanding by a factor of perhaps 10 to the 26th power or more. This is inflation, and it solves both puzzles beautifully. The horizon problem disappears because, before inflation, all the matter and energy in the observable universe occupied a region small enough that it could reach thermal equilibrium. Everything could communicate. Everything could reach the same temperature. Then inflation stretched that uniform region to cosmic scale. The far-apart regions we see today were in contact before inflation pulled them apart faster than light could follow. The flatness problem disappears because inflation stretches space so dramatically that any initial curvature becomes imperceptible. Just as the surface of the Earth looks flat when you're standing on it, even though it's a sphere, the universe, after being inflated by that inconceivable factor, looks flat at any scale we can observe. What drove inflation? A hypothetical field called the inflaton. Picture a ball sitting near the top of a very gently sloping hill. While it rests near the top, its potential energy is high and nearly constant, enough to drive exponential expansion. Eventually, quantum fluctuations nudge the ball. It begins to roll down the hill. As it does, inflation ends. The energy stored in the inflaton field converts into a burst of heat and particles. The universe lights up. The ordinary Big Bang begins. But here's where inflation opens a much deeper rabbit hole. Because of quantum fluctuations, the inflaton field doesn't end inflation everywhere at once. In some regions, the ball rolls down and inflation stops. Those regions become universes like ours. In other regions, the ball stays near the top and inflation continues. Those regions keep expanding exponentially, faster than any signal could cross them. And within those still inflating regions, more pockets stop inflating, each seeding a new universe. This process, eternal inflation, may have no end. It generates an infinite sea of expanding space, dotted with bubble universes. Our universe is one bubble, one pocket where inflation stopped and the laws of physics crystallized into their current form. Other bubbles may have different physical constants, different particle masses, different forces, or no forces we'd recognize at all. This is the inflationary multiverse. And if it's real, it transforms our question about nothing. Because in an eternally inflating multiverse, there is no beginning. Is no moment before which there was nothing. There is always something happening somewhere. A field inflating, a universe nucleating, a bubble forming. The process has no off switch. It has always been on. Let's entertain a different possibility now. One that doesn't require a beginning at all, and doesn't require some multiverse either. What if the Big Bang was not the first thing? What if it was a rebound? This is the proposal at the heart of loop quantum cosmology, a rigorous and mathematically developed attempt to apply quantum mechanics not to particles, but to space-time itself. The problem it's solving is this. General relativity, when applied to the Big Bang, produces a singularity, a point of infinite density and infinite curvature. Infinities in physics equations are red flags. They signal that the theory has exceeded its domain of validity. A singularity doesn't tell you something infinite happened. It tells you your theory has broken down. Loop quantum gravity attempts to fix this by proposing that space-time is not continuous. At the smallest possible scale, the Planck length, roughly 10 to the minus 35 meters, space is not a smooth fabric, it's granular, quantized. made of discrete loops of geometry woven into a network. Space, at the deepest level, is not a continuous field but a kind of mesh, a cosmic chainmail, if you will. When this framework is applied to cosmology, something remarkable emerges. As you rewind the universe toward the Big Bang, as it grows denser and hotter, quantum geometric effects become increasingly dominant. These effects generate a kind of quantum repulsion, a pressure that builds at the Planck scale and resists further compression. Instead of the universe collapsing into an infinite singularity, it reaches a minimum size, unimaginably small but finite, and then bounces. The collapse reverses, expansion begins. The Big Bang in this model is the big bounce, not a creation from nothing, a turning point. Before the bounce, a contracting universe, perhaps with its own billions of years of history. Galaxies falling inward, stars compressing, space folding, eventually reaching the quantum threshold, and then bang, rebound, a new expansion, our universe. If the universe can bounce once, it can bounce again. And if it bounced before our universe, perhaps it bounced before that universe too. A cycle of expansions and contractions, each one giving rise to the next. No first cause, no origin from nothing. Just an eternal heartbeat, the universe inhaling and exhaling across unimaginable stretches of time. Can we test this? Possibly. Loop quantum cosmology predicts specific imprints in the cosmic microwave background. Subtle patterns in the polarization of that ancient light that would carry information from before the bounce, transmitted through the quantum geometry of the bounce point itself. Current telescopes aren't sensitive enough to detect them clearly, but future missions are being designed with exactly this in mind. In 1983, James Hartle and Stephen Hawking published a proposal that approaches the origin of the universe from a completely different angle and arrives at one of the most quietly revolutionary ideas in the history of physics. They called it the no-boundary proposal, and its central claim is this: the question, what came before the Big Bang, is not just unanswerable. It may be meaningless, not because we lack data, but because the geometry of time near the beginning has no edge to come before. To understand how they got there, we need a brief visit to a technique in quantum mechanics called the path integral, developed by Richard Feynman. In quantum mechanics, particles don't follow single definite paths from one place to another. They explore all possible paths simultaneously. The actual behavior we observe is a sum, an average, over every possible trajectory, weighted by the probability of each. This is the path integral formulation, and it lies at the heart of quantum field theory. Hartle and Hawking extended this framework to the universe itself. To calculate the probability of the universe having a particular configuration, a particular geometry of space-time, you sum over all possible histories, all the ways space-time could have evolved to reach that configuration. When they did this calculation, using a technique called imaginary time, a mathematical rotation that converts the time axis into a spatial dimension, they found something astonishing. Near the Big Bang, the geometry of the calculation became smooth and rounded. There was no singularity, no sharp point, no edge. The origin of the universe, in their model, looks like the south pole of a sphere. Think about what that means. Ask yourself, what is south of the South Pole? Nothing, not because there's a wall, not because it's forbidden, but because south simply stops meaning anything at that point. You can walk in any direction from the South Pole and you'll be walking north. The concept of further south doesn't apply. The geometry just rounds off. Hartle and Hawking proposed that the beginning of time is like that. Not a moment you could reach and look behind. Not a point at which something started. Just a region where the usual concept of before becomes geometrically meaningless. Time doesn't end at a wall. It curves smoothly into space. The question, what came before the Big Bang, becomes as incoherent as what is south of the South Pole. Grammatically possible, physically senseless. In this model, the universe is finite but unbounded. It has a finite duration but no edge in time. Just as the surface of the Earth is finite, it doesn't go on forever, but has no edge you could fall off of. The universe has a beginning that is, in a geometric sense, just the rounded tip of its time dimension. This is beautiful, and it doesn't require an external cause, a prior universe, or a quantum tunneling event. The universe, in Hartle and Hawking's model, is self-contained. Its laws, structure, geometry, and history all emerge together, no boundary, no before, just a smooth, self-enclosed existence. Let's travel now into the most speculative, but also among the most mathematically serious territory in modern physics. String theory began as an attempt to solve a specific problem: how to reconcile general relativity with quantum mechanics. These two theories are the twin pillars of modern physics, and they are fundamentally incompatible with each other. General relativity describes gravity and the large-scale structure of the universe as the smooth curvature of space-time. Quantum mechanics describes everything else: particles, forces, fields, in terms of probability and discreteness. At ordinary scales, you can use one without worrying about the other. But at the Planck scale, in the heart of a black hole, or at the beginning of the universe, both become relevant simultaneously, and they contradict each other catastrophically. String theory proposes a resolution. The fundamental objects of nature are not point-like particles. They are one-dimensional vibrating strings, loops or strands of energy oscillating at different frequencies. Each frequency corresponds to a different particle. An electron is one vibrational mode. A photon is another. The graviton, the hypothetical carrier of gravity, is yet another. Gravity is not separate from the quantum world. It emerges from the same framework as everything else. The catch: the mathematics of string theory only works in 10 or 11 dimensions. The extra 6 or 7 dimensions beyond the 4 we experience are compactified, curled up so tightly at the Planck scale that they're completely invisible to us. Present everywhere, but inaccessibly small. Like the circular cross-section of a garden hose that looks like a line from a distance. In more advanced versions of the theory, collectively called M-theory, strings give way to higher dimensional objects called brains. Our universe, in some models, may itself be a three-dimensional brain, a membrane floating in a higher dimensional space called the bulk. We're stuck to our brain the way a drop of water is stuck to a glass surface. We can move freely along the brain, but we can't step off into the bulk. The extra dimensions are there, but unreachable. And sometimes, brains collide. This is the ekpyrotic model, proposed by physicists Paul Steinhardt and Neil Turok. In their scenario, what we call the Big Bang was not a spontaneous creation. It was a collision between two brains drifting through the bulk. When they met, the impact released an enormous burst of energy, heating the universe, seeding it with matter and radiation, setting off the expansion we observe today. The Big Bang was not a beginning from nothing. It was a contact event in a higher dimensional space, and after the collision, the brains drift apart, slowly, pulled by the faint residual forces between them. Eventually, they slow, stop, and begin to drift back together. They approach again, they collide again, another Big Bang, another universe, another cycle. In this picture, the Big Bang is not singular, it is recurring. The universe has no first moment, just an endless sequence of collisions between brains in a higher dimensional space that has, itself, always existed. Physics can model the vacuum and calculate the probability of quantum tunneling. But there's a question it hasn't answered. A question that may be beyond its reach. Why does anything exist at all? This isn't a physics question, it's a philosophical one, and philosophers have been wrestling with it for more than 2,500 years. We begin, as so often, in ancient Greece. In the 5th century BCE, a philosopher named Parmenides of Elea made a claim that sounds almost circular, but is deeply, stubbornly important. Nothing cannot be. His argument, to think about nothing, you need something to think about. The very act of contemplation requires a subject. You cannot have a thought that is truly about nothing, because the moment you direct your mind toward it, it becomes something, the object of your thought. Nothing is self-defeating. To speak of it is already to betray it. Parmenides concluded that reality is a single, unchanging, eternal whole. Change, birth, death, motion, all illusions created by our limited senses. Only being exists. Nothing is not just rare or hard to find. It is impossible. His near contemporary, Heraclitus, took the opposite view. The world for Heraclitus was constant change, ceaseless flux, eternal becoming. You cannot step in the same river twice. The universe was not a frozen unity, but a living tension of opposites. Light and dark, hot and cold, presence and absence. He didn't argue for nothingness per se, but he made room for it, insisting that absence was as real and meaningful as presence. Later, the atomists, Leucippus and Democritus, took the most practical view of all. They needed nothing, quite literally. Their model of reality required a void, empty space through which atoms could move, collide, and combine. Without nothingness, without a genuine vacuum, matter couldn't travel, couldn't interact. The world couldn't work. For the atomists, the void wasn't a metaphysical embarrassment. It was a physical necessity. Aristotle disagreed, and his disagreement shaped Western thought for over 1,000 years. Nature, he said, abhors a vacuum. Every region of space must be filled with something. His reasons were partly physical. He didn't believe in action at a distance, so there had to be some medium carrying forces, and partly metaphysical. A truly empty space would have no properties, and something with no properties can't meaningfully exist. The void was a logical contradiction dressed up as an empty room. Medieval scholastic philosophers largely followed Aristotle. The universe was full. God was the ultimate fullness of being. Nothingness was the privation of being, not a thing in itself, but the absence of the real. The scientific revolution cracked this consensus. By the 17th century, Evangelista Torricelli had created a physical vacuum in a mercury tube. Blaise Pascal confirmed it and investigated its properties. Empty space, in the physical sense, was demonstrably real, or at least real enough to measure and work with. But the deeper question, what about absolute nothingness, remained untouched. René Descartes, for his part, was deeply uncomfortable with true emptiness. His famous cogito ergo sum, I think, therefore I am, grounded existence in the act of thought. But for Descartes, space and matter were inseparable. Wherever there was extension, wherever there was space, there had to be something occupying it. Pure void was incoherent. It was left to the 20th century, and to Martin Heidegger, to bring the question of nothing back to the center of serious philosophical attention. In his 1929 lecture, What is Metaphysics?, Heidegger urged his audience, and through his writing, all of us, to actually face nothingness, not to explain it, not to classify it, but to stand before it in the full weight of its strangeness and feel what it means. He argued that the experience most conducive to this encounter was existential anxiety. Not fear of a specific thing, a snake, a job interview, a difficult conversation, but the peculiar anxiety that has no object. The dread that sometimes arrives in the quiet hours without a specific cause. In those moments, Heidegger said, the world of ordinary things withdraws. Nothing feels solid. Nothing seems guaranteed. And in that withdrawal, we get our only direct contact with the possibility that things could not be. that existence is not inevitable, not automatic, not guaranteed. Why is there something rather than nothing? Leibniz asked it in the 17th century. Heidegger made it visceral in the 20th. And the question remains open, not because we haven't thought hard enough, but because it may be pointing at something our concepts cannot fully grasp, something at the limit of thought itself. Here's a possibility that flips the entire inquiry upside down. What if nothing is not just physically impossible, but logically incoherent? What if asking, why is there something rather than nothing, is not a deep question, pointing toward an answer we haven't found yet, but a grammatically valid question built on a faulty premise? Consider how we use the word nothing in everyday life. There's nothing in the fridge. Nothing happened today. I have nothing planned for the weekend. In every single case, nothing is a relational concept. It describes the absence of a specific thing we expected or hoped to find. The fridge still exists. The day still passed. The weekend is still full of time. The nothing is always relative, nothing of a certain type, in a certain context. When we extend this to the cosmos, when we try to imagine a nothing, that is not just the absence of something specific, but the absence of everything, including space, time, laws, and logical possibility itself, we are stretching a relational word well past its breaking point. We're asking a word that only makes sense in context to describe the total absence of context. Some philosophers of language argue that absolute nothingness is not a description of a possible state of affairs. It's a grammatical structure that looks like one. The sentence, "nothing exists," sounds meaningful, but on close examination, it requires a referent, some framework in which the nothingness of things can be established. A state in which nothing is the case is still a state, and a state is already something. Physics, fascinatingly, seems to agree. Every time physicists attempt to reach true nothingness, to empty space of everything, to strip away matter and energy and fields, something remains, a minimum energy, a fluctuating vacuum, a background geometry. The quantum fields that permeate space cannot be switched off. The Casimir effect is real, the Lamb shift is real. Virtual particles are real in their effects. Nature, as far as we can tell, has no off switch. Even the lowest energy state of reality is a something, humming, uncertain, filled with the ghost energy of fields that simply cannot be quieted. If that's true at the physical level, and if it's also true at the logical level, if absolute nothingness is not just rare but incoherent, then the question, why is there something rather than nothing, rests on a false premise. It assumes nothingness was an alternative, but what if it never was? What if the very laws of logic and mathematics are so fundamental that they couldn't be absent? And what if a universe, or at least some form of structured reality, is a necessary consequence of those laws existing? This turns the traditional mystery on its head. Instead of asking why the universe exists, we might ask, what is the nature of this necessary, eternal, self-sustaining something? And what does it mean for us, brief arrangements of matter capable of wondering about it, to be part of it? Let's rest for a moment on the quietest and perhaps most profound possibility of all. What if something has simply always existed, not created, not tunneled into being, not born from a collision or a bounce, just there? An eternal presence that requires an origin because it was never absent, an existence that needs no explanation for its beginning because it has no beginning. This idea, that something is eternal, appears in many forms across the history of thought. Religious traditions have often placed an eternal creator at the source. Some philosophers have proposed eternal mathematical objects or abstract structures. And now, in modern cosmology, a number of serious models allow for a reality that has no true first moment. The inflationary multiverse, as we discussed, has no beginning. Eternal inflation is always happening somewhere. New universes are always nucleating. There is no edge in time where the process started. Loop quantum cosmology proposes a universe that bounces eternally. No first bounce, no original expansion, just a cycle without a starting point. Some interpretations of quantum gravity suggest that time itself is an emergent phenomenon, not a fundamental ingredient of reality, but something that arises under certain conditions from a deeper, timeless substrate. In that case, asking what came before time existed is like asking what happened before wetness. The question assumes a property that wasn't yet defined. And there's another possibility, quieter still. What if the laws of mathematics and logic, the abstract structures that govern what is possible, are eternal in the most basic sense? Not eternal in time, because time might be a local feature. Eternal in the sense of being necessary. True in all possible circumstances, unable to be otherwise. If mathematical truths are necessary and eternal, and if they allow, or even require, a physical universe of some kind, then the universe's existence might not be a surprise at all. It might be the only coherent option. The way 2 plus 2 4 is not a surprising coincidence but a necessary truth. Not contingent on anything, not dependent on when or where you check. In that view, asking, why does the universe exist, is a bit like asking, why does mathematics work? The question assumes it could have been otherwise, but it couldn't. The structure of logic and number, whatever they ultimately are, simply is. And if a universe is a consequence of that structure, then the universe simply is too. This doesn't resolve the mystery. It transforms it. Instead of why is there something rather than nothing, we arrive at what is the nature of this something that couldn't have been otherwise, and what does it mean to be a brief, conscious part of it? That question has no clean answer. But it feels like the right shape for the question we're actually asking. I want to take a moment here to step away from the physics and the philosophy and address something more immediate. You might be wondering, reasonably, with great practicality, whether any of this matters. You have a day tomorrow. There are things to do, problems to solve, people to attend to. Whether the universe tunneled from nothing or bounced from a previous cosmos has no bearing on whether your coffee tastes good in the morning.
Fair.
And I'm not going to pretend otherwise. But I do want to argue for something subtler. These questions, the ones at the absolute limit of what can be known, do something that more immediately practical knowledge doesn't. They change the scale at which you experience your life. When you genuinely absorb the possibility that time might have no beginning, that your few decades of experience are set within a context that may be genuinely eternal, or may have collapsed and expanded billions of times before producing this particular universe with its particular stars and its particular planet, something shifts. The things that feel urgent often feel slightly less so. Not because they don't matter, but because you see them more clearly in proportion. When you absorb the fact that you are made of atoms forged in stellar cores, that the calcium in your bones was synthesized in a dying star before the Earth existed, that the iron in your blood was produced in a supernova that scattered its contents across light years of space before gravity gathered some of it into the solar nebula that became your world, you don't feel small. You feel continuous. You feel woven into something vast. And when you sit with the possibility that nothing, true nothingness, may never have existed, that something has simply always been, you feel something else too. Something harder to name, but real. A sense that existence isn't fragile or contingent or likely to be snuffed out into void, that whatever we are part of something that persists. That the universe, whatever its shape and history, is not a brief flicker in an infinite darkness. It may be the darkness itself transformed. These questions are not separate from life. They are life at its most wide awake. They are what happens when the human mind, shaped by evolution to track predators and plan for winter, turns its attention away from the immediate and asks the deepest thing it knows how to ask. What is this and why? Every culture that has ever existed has had creation stories, myths of origin, explanations for why there is a world. We are apparently a species that cannot stop asking. And in that asking, in that insatiable, sometimes inconvenient curiosity, there is something worth honoring, something that distinguishes us from every other arrangement of matter we know of. We are the universe looking at itself, asking itself questions it can't fully answer, wondering at its own existence, and finding in that wondering not frustration, but something that feels remarkably like home. So, here we are, at the end of a long journey through very deep water. We've walked through quantum fields and ancient Greek philosophy, through a universe born from tunneling probability and a universe that bounces eternally with no beginning. Through brains colliding in hidden dimensions and time rounding off like the tip of a sphere. We've asked whether nothing is the correct name for empty space, and found that empty space is not empty. We've asked whether nothing can logically exist, and found that language itself might be playing tricks on us. And what have we arrived at? Not a clean answer. Honestly, not much of an answer at all, in the traditional sense. But something I think is better, a richer set of questions, a more precise sense of what we don't know, and why that not knowing is interesting rather than frustrating. Maybe the universe tunneled from quantum probability. Maybe it bounced from a previous cosmos. Maybe it's one bubble in an eternal inflationary sea. Maybe it has no beginning because time itself has no edge to begin at. Maybe something has simply always existed and nothingness was never coherent enough to be a real alternative. We don't know, and I want to say clearly, that's okay. Not knowing is not a failure. It's the correct epistemic response to a question this large. The mystery at the origin of everything is not a gap we've failed to fill. It's a horizon, always present, always receding slightly as we approach, always revealing new terrain between here and there. And the journey toward it, however incomplete, is one of the finest things a conscious mind can undertake. Because in following these questions, you've done something remarkable. You've held in your mind, a mind built by evolution for finding food and avoiding predators, the possibility of infinite universes, the geometry of time, the restlessness of the quantum vacuum, the brains drifting through hidden dimensions. You've thought about nothing and found that it refused to stay nothing. That's not a small thing. That's one of the most distinctly human things there is. So, as you close your eyes tonight, let the questions float. Don't try to solve them. Let them drift, like stars you can only seek when you're not looking directly. They'll still be there in the morning, patient, luminous, full of the same strange beauty. And if you wake in the night and the question drifts back, did nothing ever exist? You can smile and know that you've looked into it more carefully than most, and you've found something true. That wherever you look for nothing, existence keeps showing up instead. Stubborn, radiant, impossibly here. Good night.